Okay, testing, testing. That's good. All right, class, can I get everyone face this way? So have a look at the graph here. Actually, just give me a moment. I'm going to change the lights.
My headphones in class.
It's a microphone for me. I'm not listening to music. This is my microphone. You can use your Apple headset as a microphone as well. Yeah, so I'm breaking the rules, that's right. So there's rules for me and there's rules for you. And sometimes they're different. I have a reason and I set the rules. Okay, most of them anyway. Okay, so everyone can see that? It's pretty sharp? Yeah. Okay, so I'm doing this because I'm testing out a few things. I did this with the Year 12s today. Recording what basically I'm projecting on the screen. So you guys can watch this afterwards. It'll be good for people who aren't here today. All right. So we've gone through displacement time graphs, and I like to leave a bit of a gap between that and velocity time graphs because they're actually very different. We're measuring a different variable, and there's completely different circumstances about what these all mean. Okay, so when we went through velocity time graphs, I'll say that again. When we did displacement time graphs, what was represented by the slope? Does anyone remember that? Pardon? Actually, that's what this one will be. When the displacement time graphs, the slope was your displacement over your. So your displacement was up, and that was your time was across, and that was velocity. This case, it's velocity over time. So yeah, you're right. It's acceleration this time. So the slope demonstrates acceleration. So we can work that out. So for example, in this first section here, I'll grab my pencil. Okay, so this first 5 seconds, okay, we start at 0. What do you think that means? 0 what? You're not moving, you're stationary, but we are accelerating. After 5 seconds, we reach 10 meters per second. What do you think is special about it being a straight line? Constant acceleration, good. All right, so let's work out that acceleration. I'm just going to write on top here, so this little segment here. All right, so we go from acceleration is velocity final minus velocity initial. Remember, those are vectors over change in time. Okay, so that is, over the first 5 seconds, 5 minus 0 on the bottom, and we've got 10 meters per second minus 0. So 10 over 5 is 2 meters per second squared. Okay. You happy with that? All right. Now, what do you think that's special about that section there? It's not. Is it stationary? Nearly. Velocity. Yes. Now you see, I've got on my graph here, I've got a positive, which is east, and negative axis. So actually, I should put negative signs on there. Yeah. So it's actually velocity because there's actually 2 segments. If the graph is only kind of one bit above the time axis, you could say speed. Yeah. But in this case, we have a constant. Yeah, someone said displacement or stationary. That's true for the displacement time graphs. Now we're doing velocity time graphs. So you have to check at the top, are you talking about velocity or are you talking about displacement? That's why we spent a bit of time on displacement when we did some other things. We did vectors. Now we're coming back to graphs again. So this helps break it up a bit. When I do it all at once, I find people get very confused. Constant velocity. And that's a velocity of 10 meters per second. Actually, I should put a vector in that. Acceleration is east, and that's also east. Okay. So you have enough of that? Okay. Now, let's work out this segment. All right. So let's think about this. Okay. I'm going to break this up into 2 bits, but I'm going to calculate the acceleration of all of it. All right. Now, let's think about this. This segment here. I'm just going to this segment from there to there. Okay. You're going towards the time axis. Now, this is what does a lot of people's heads in, and it's more of a problem for those who do this in maths. You do this in maths, and you also do this in physics. Is my velocity increasing or decreasing? Decreasing. Okay, that's right, because the graph's going down. That's going to confuse you in the next bit. Is my speed increasing or decreasing? It's actually decreasing still. It's basically, the speed is the magnitude of velocity. That's actually going to be more confusing in the second bit. So in this first bit, I'm going from 10 meters per second to 0 is about there. So I don't know, that's kind of, if that's 11, it's between 11 and 12 seconds, it will actually be 0 for a moment. So it's actually slowing down. So you can think about this like a ball going up in the air and then coming back down. That's not quite what this is, but it's a decent enough analogy. So we have speed and velocity decreasing. Now, I'm going to bring this up a little bit. Just going to move the camera so I can look at the bottom bit of the graph. Okay, so let's work out this acceleration. All right, now it's all one line, so I can work that out in one hit. So what is my final velocity? Minus 20, thank you. Yeah, minus 20. Yeah, see, I intentionally did this on graph paper so you guys could spot it a bit better. So minus 20. Okay, so yeah, it's minus 20, not positive 20. Minus initial, negative 10, divided by the interval of time. We do this at 15 and take 10. Okay, so that's minus 30 over 5, which is negative 6 meters per second squared, or in the context, what is it? 6 meters per second squared, what direction? That's east, the top one was east, so the opposite direction would be west. Yep. Okay. All right, now let's think about this segment. So that's for the whole thing. Okay. Now if I just take this segment and that segment. Okay, this segment here. All right. Okay, now this is going to do your heads in, so I'm just going to show this once, and I'm probably not going to even ask you about this again in a test. The one you have to worry about is the speed when it comes to this one. Okay, now, purely as a mathematical thing, because your graph is going down, technically speed is decreasing. You start with, like, if you start here, you've got a small negative number, and then you get a big negative number. So you're traveling further negative on your number line. So if you do this in mass, that would be velocity is decreasing, because you're going down. But speed is the magnitude. Are you getting a smaller magnitude or a larger magnitude? Larger. Your speed is increasing. Okay, well, I'm glad. I heard someone say that makes sense. All right, yeah, that's the way to think about it. Okay. Now what's happening here at the bottom? Constant velocity at 20 meters per second west. No, the bottom, the below here is actually west. Okay, because that's negative. So if you go back to the top, I said velocity meters per second east. Now, if I got a negative velocity towards the east, that means I'm going positive to the west. Okay. So remember, we can use the different signs to represent one-directional motion in one-dimensional motion in two directions. Okay, yeah. So everything below the axis is motion in the negative direction. Everything above the axis is motion in the positive. Now we're going to do a few tricky things. We've been dealing with the slopes. This is this graph is actually really special for those of you who are going to go on to do like year 12. I think you guys would be doing year 12 methods, not studies, because they're just changing the course. All right, this is actually pretty cool because it demonstrates both differential calculus and integral calculus. We're doing the differential calculus by doing the slopes. It's easy because it's all straight lines. Calculus gets harder when it's curves. But we're going to do integral calculus by working out the areas. And you see what I mean about east and west. All right, now just do the last segment. Actually, there's two more segments. There's also the bit at the end, because I did that in pen. I know it kind of all looks the same on here. But the last, okay, there's another 5 seconds there. 1, 2, 3, 4, 5. That's 30. Okay. All right. So the last bit is basically the reverse. No, it's not, sorry. We got to change. So let's just do one more acceleration. You've done it a few times. Let's just do it one more time. Okay, now, again, just pay heed to the signs. our final is 0 meters per second. Our initial is minus 20, but it's final take initial. You see that? Minus, sorry, my hand's in the way. Minus negative 20. Final take initial. Yep. Okay. And then time, 25 take 20. We've got positive 20, negative, negative, make it positive. 20 over 5 equals 4 meters per second squared equals 4 meters per second squared in the east. Okay. Now I won't necessarily write it on there because I've got, yeah, there we go. All right. Okay, so what do we reckon about that one? Are we increasing our velocity? Yes. Are we increasing our speed? No. We're going towards, okay, the way to remember that, are you going towards the time axis or away from it? Because if you're going towards, the numbers are getting closer to 0. You're traveling in the negative direction. Yeah, because you're going up the graph, technically it's increasing in that mathematical sense. But if you think about velocity, if you think about speed, so here you're traveling at 20 meters per second west, at the end you're traveling at 0 meters per second anywhere. So your speed is decreasing. Yeah. So that's a bit of a tricky one. So I've asked you that 3 times, and it takes a while to make sense of that. It's probably better just to think of that in terms of speed instead of velocity. Because when you start doing this in 2 dimensions, you can have a changing velocity without actually changing the magnitude of speed at all. That's circular motion. Uniform circular motion, I should say. Now, what do you think is happening in this interval? Sorry? Nothing. Okay, I think I know where you're going with that. Just a bit more detail.
Isn't that moving
at... Sorry. No, it's 0, that line. So the axis is drawn on... Oh, sorry. I mean, I've kind of... I'm talking about that's the last bit of the graph, is there. So it's on the axis, so what does that mean? It's not moving, stationary. No, that one. So I'm just using that as an interval to mark that out. Sorry. Okay. Yeah, I didn't join the graph up there. All right, sorry. I understand ambiguity. Yeah, you'll be right. If the graph started just jumped up there, it'll be moving at 5 meters per second to the east. You're right. Okay. No. It's just I'm just using that as a comparison of this segment. So that's the last bit of the graph. It's just hugging the time axis for 5 seconds. So that actually stays stationary. Okay. Now, first question is, okay, when are we stationary? Have a think about it. Ah.
At the start and at the end.
Okay, so we had the start, so that's correct. Sorry, actually you can't see the question. That's all right, so I scribbled it out. When are we stationary? Okay, at 0 seconds. Where else? Sorry. Yeah, 25 to 30 is definitely true, from the interval of 25. And about, I would estimate it, time is approximately
11 3/4.
11 3/4 is probably about right. So 11.75. I'm just approximating that. So sorry. Okay, that's the 3 times. So there's 2 times where we're instantaneously stationary. So just for an instant, like you throw up a ball, it's instantaneously stationary for that moment. So I just show the graph a bit more. All right, so we got that at the start, and also we're also here because we changed directions at that point. So we go from traveling east to traveling west. We slow down in the east, we turn around and start traveling west with the same acceleration, but now we're picking up speed. Okay, now also at the end, for 5 seconds we are stationary, and we stay stationary for 5 seconds. And that's the end of our story. Okay. All right, now another one. All right, next thing we're going to find is our total displacement. All right, guys, just pay attention. Watching this way. You're going to be doing it yourself in a minute. Okay, so I'll show you how this is done. what we can do is we're going to break this up into... Someone's asleep at the back. Do you want to just give them a tap? Thank you. All right. So, yeah, that's all right. So I want you to get you guys doing this yourself in a minute. So the faster I get through this, the sooner you get some practice. All right. So the way you'd have to do this, I'm going to definitively call that 11.75 for the calculations. I didn't actually realize I had to do that, but I do. Okay, that's what you get for just making up questions on the spot. All right, so we have to work out, let's just work out the east, which is these three parts. Okay, so the way that we're going to do this, if you think about this, I'm traveling at start 0 meters per second, at the end 10 meters per second. On average, I'm traveling 5. Does that make sense? For 5 seconds. So I was traveling at 0 to start with, and I accelerate up to 10 meters per second. That's actually the same as traveling 5 over that whole thing. You can actually work out that area would be exactly the same thing. Guys, pay attention. Santiago, turn around. All right. So what I'm going to do is calculate. That ends up being the same. So in our total displacement, we've got, I'll just call that A, B, and C, just for the sake of following this. All right. So the east, we're going to work out those three areas. So we work out triangles by half times base times height. So half, so go back to the graph, half of 5 times by, half base, that's right, half of 5 times by 10. Okay, so half times 5 times 10 plus, so that's A, B would be, now that's just a rectangle, so 5, the gap in that time is 5 times by 10. 5 times 10, and okay, the interval there, you probably have to pull out your calculators for this one, that triangle is 1/2 times by, the interval from 0 to 11.75 is 1.75, times by 10. Okay, 10 in height. All right, so that's 5 times 10, sorry, just go back to the calculation. 5 times 10 is 50, half of that is 25, plus 50, okay, half of 10 is 1.75, I'm going to grab my calculator. Times 0.5 times 10. Okay, that last bit there, guys, keep the noise down. 8.75. All right, so did everyone see what I've done there? I've gone and I've worked out the areas of A, B, and C. That represents the motion in the east direction. Now it's important that you separate this. When displacement, you separate the east and the west, or whatever context you're doing. It has to be. You have to separate the negative areas and the positive areas, because negative areas would be in the positive areas, positive direction motion, and negative part, that will be that area. The area will be displacement in that direction. So if I work that in total, 25 plus 50, 75. 83.75 meters east. Okay, that's the first part. And then we've got the west. Let's work out the west. All right. So let's just go quickly have a look at my west section. That's that bit. Now, if you want, you can break that into triangles as well, but that's a nice shape in itself. So there is actually the Trapezoid Rule as well. If you know how to use that, you can. If not, well, basically I'll show you. So I'm just going to work this out in one hit. So I'm going to call that, sorry, I can't see that. I'm going to call that length A across there, that time length. And on the bottom, it's length B, and that's going to be my height. Okay, is everyone happy enough with what I've done with that? Okay. Now, the formula for that is the average of A and B. This is the Trapezoid Rule. Average of A and B times by height. Okay, let's work that out. So A is, let's go back to that. All right, so it's 11.75 and 25. All right, so I'll subtract that. 25 take 11.75 is 13.25. Okay, and the bottom part is just 5 seconds. Okay, so B is 5, A is 13.25, and the height is 20. Okay, so let's substitute that in there. 11.25 plus 5 over 2 bracket times by, whoops, what was it, height? 20, thank you. All right, so you can work that out. 11.25 plus 5 is 16.25, divide that by 2 is 8.8 and an eighth, 8.125 times by 20 is 162.5. Okay, so what do you think that means? Well, no, because it's, all right, if you look at the graph now, I think you're still thinking in terms of displacement time graphs. If this is a displacement time graph, you'd be correct, because you come back to where you started. It's a velocity time graph. Yeah, it's basically, no, if you worked out the total acceleration, like over the 30 seconds, that would actually be 0, because you end up at the same speed as what you started. All right. I'd say if you work out the change in velocity over the whole thing, that would end up being 0 as well, over that 30 seconds, because you do end up at the same speed as what you started. But distance is worked out by these areas. Okay, so we got that, and that one was west. Okay, so what do you think? How do we work out, with those two, how do we work out the displacement they've actually traveled? What can we do with those vectors? We've got displacement east, displacement west. What do we do? Add them. Well, we vector add them, so what do we actually do with the numbers? Oh, think about it this way. Okay, now I've chosen west to be, east is positive, so displacement, I'll vector sum them, so I would have positive, sorry, can't see that. Let's move you over. There we go. Okay, so we get positive 83.75 meters minus, plus negative, because west is the opposite direction, yeah? So we are taking a vector sum, but it ends up with the operation being a subtraction. Okay, meters. All right. All right, so 83.75 minus last answer is negative 78.75 meters. Okay, and let's put that into context. What does that mean in context? Yeah, from wherever you started, you've moved west by 78.75 meters. Okay, because the result ended up being you spent more motion west than you did east. Yeah, is that making sense to people? Okay. All right, so a follow-on question to that, I might just move the camera over this side. Okay. Okay, what about the total distance? What do I do to work out the total distance traveled? So we had motion east, we had motion west. Do we care with total distance, which direction it goes? No, we just add it up. So let's just do that. 83.75 plus 78.75 equals sorry, that was the final answer. Whoops, wrong one. Sorry, plus 126.5. That was it.
162.
Yeah, 162.5. Wasn't that the west? Yeah, that was the final result of the displacement. Sorry, wrong one. All right, guys, keep it down. You're distracting me. Okay, one more thing I'm going to do after this, and then you guys will try it for yourself. Okay. All right, so total motion, total distance traveled, 246.25. Okay, you have enough of that? We just added up what we traveled east with what we traveled west. Okay, now a couple things you could do with that. I don't necessarily think you need to go through it, but if we go the average speed, maybe I'll get you guys to calculate yourself. All right, 146.25. So I'll say 0 to 30 seconds. Average speed, divide that by 30, and average velocity would be the velocity traveled, sorry, the displacement, so 78.75 over 30 meters per second west. Okay, so if it, yeah, same concept for 0 to 30. Okay, so I went through that pretty quickly. So just to give you guys a bit of background how to go about doing those problems, you can watch that a couple of times because this is going to be available in the future. So let's finish that off.